Using the semantics of the database, which means during that requirement analysis phase, when we talk to the customers, we are going to form some of the FDs, like using the student ID. They may say that student is going to have unique ID. Then using the student ID, we may say every student ID can determine student name, and every student ID can determine, let's say, his address, his phone number, like that. So I'm going to come up with some of the functional dependencies using the semantics, that is called as semantics, meaning, right? So meaning is going to give me the basic set of functional dependencies, and after getting that basic set, I would like to do many things before going ahead with the normalization. So these functionalities which I require, or the operations which I perform on functional dependencies, are like this. One is identifying the additional functional dependencies, which means even though we got, let us say, some of the functional dependencies, using them I could even derive lots of functional dependencies. So I want to know what are the additional functional dependencies I could derive, and I want to derive all of them. Okay, and let us say identifying keys means the candidate keys. So you know the key concept, right? So I want to identify what are the candidate keys using functional dependencies. This we didn't see before, but this is a very interesting technique, and we are going to use it once we know the functional dependencies. While we start the construction of relational database, one way to get the key attributes is by the meaning of it, and the other way is you get the functional dependencies and you can run some algorithms on it, and you can even find out the candidate keys. That is one other way, we shall see it. Next one is identifying equivalences of FDs, which means they will give you a set of FDs and other set of FDs, and they'll ask you whether both are semantically equivalent. Sometimes what happens is the same meaning of the functional dependencies, whichever is expressed in one form, can also be expressed in other form. I'll just give you an example. See this. Assume that one set contains A derives BC and D derives EF, right? This set and the other set contains A derives B, A derives C, D derives E, D derives F. Now these two sets, even though they look like they are completely different FDs, they are actually same, they are equivalent. That is what we should identify. I want to identify whether two sets of functional dependencies are equivalent or not. Why I want to do it is, maybe I want to go with the smallest FDs possible, right? And next one is, I'll try to find the minimal FD set, which means I'll try to minimize. Sometimes what happens is, some of the functional dependencies turns out like they are not required. For example, in this functional dependency, if I write A derives B, already A is deriving BC, here again A is deriving B, so it turns out that you could actually delete this FD, right? So I want to identify such things and I want to delete them. So whatever it is, what I mean to say is, we want to perform various operations on functional dependencies before we actually go for normalization. What is normalization? Splitting up the tables, dividing the tables into various tables. Before I do that, I want to perform various other activities, so that normalization will be easy. Now in order to perform all these activities, we have two well-known methods. One method is, you can use the inference rules. Inference rules means there are some set of rules which are already specified. They are like theorems. You can use those theorems and you can use the results, and you can go ahead with doing all these operations. That is one way. And the other way is using closure set of attributes. Closure set of attributes means, okay, I'll tell you later after this. Anyway, these two are popular methods, but then in coming to gate, if you use inference rules, it is going to take a lot of time. So we are not going to use inference rules at all. I'm going to say what are the inference rules and what are the various theorems available there, or the various types here. We shall see them, but then we are not going to use them in problem solving, either in gate or in interviews. Never use them. Okay, we are going to use the shortest form, which is a closure set of attributes. One good thing about closure set of attributes is, it is not just easy, it is not error prone. If you go with these inference rules, you might have to apply many rules before you come to the conclusion, and there are lots of chances that you might commit some error there. Therefore, the error prone method is using the closure set of attributes. So we shall use this extensively in this course, not just for Git. It is useful even for the real world database design also. So if you become a database administrator and if you are planning to design a database right from the basics, the schema and all, you go with the attribute sets, okay, closure set of attributes. Many people use that, and there are even programs and algorithms which are specifically written, which will act on the closure set of attributes only, right? So even though this is theoretically proposed and it is a formal framework, practically everyone is using closure set of attributes. Okay, anyway, I'll tell you what that is. First, let's finish it off. Okay, now inference rules means what do you infer from existing functional dependencies, right? Reflexive is nothing but let's see this. A determines B if B is a subset of A. It means that if this one is already present in this one, that is trivial, isn't it? Therefore, every trivial dependency is always true. That is what they say. So if left side is a superset of right side, or if the right side is a subset of left side, it means that whatever you wanted is already present here, so it need not determine anything, right? It always holds. It is called as reflexivity. And next one is transitivity. You must be knowing about this transitive relation earlier also, right? If A determines B and B determines C, then A determines C. That is the rule of transitivity. Given a value of A, if you are able to uniquely get a value of B, right, and given a value of B, if you are able to get a unique value of C, then definitely given a value of A, you will be able to get a unique value of C. How? First give the value of A and get the value of B and take that value and give it here, and since this relation holds, you are going to get a unique value of B. Therefore, for a given value of A, you will get a unique value of B, which means in case if these two holds, if this one and this one holds, then this one holds true. That is the meaning of transitivity. And decomposition. So decomposition means if A is capable of deriving B and C, right? If A can determine the values of B and C uniquely, then A can determine the value of B as well as A can determine the value of C independently also. Which means if you give a value of A, it is going to give you the unique set of values for B and C. Then obviously it is going to give you unique set of value for only B as well as only C, isn't it? Therefore, if A determines BC is true, then A determines B and A determines C is also going to be true, right? And next one is augmentation. Augmentation means adding, right? See this. If A determines B, then AC can determine BC. The reason is, given a value of A, you are going to get a unique value for B, right? Then given a value of A and C, you can get a unique value of B and C. It is just logical, isn't it? I don't know how to explain that also. It is just intuition, right? Augmentation, nothing. You're just putting the C's here and there, right? And moreover, that is not non-trivial also, right? That is semi-non-trivial. Next one is union. So what is union? If A can determine B and A can determine C, then A can determine BC. It is just the reverse of this augmentation, right? And next one is composition. Composition means adding them, right? If A can determine B and C can determine D, then AC can determine BD, right? These are all the rules which are actually logical also, right? In case if they ask you in the exam about any of the properties, you can directly write them. Just by the name itself, it indicates what the meaning of it is. So by combining these rules, they have derived even some few more rules which are not very important. They are composite. These are the basic rules, right? So what I mean to say is, you just know about them. In case if they ask in the exam directly about inference rule, you'll be able to write it, sure. But then we are not going to do any problems on this, especially this kind. We are going to do everything of written here using closure set of attributes only, right? It is very interesting, and I'll tell you how to do it now. Okay, we shall move on to closure set of attributes. Fine.